This is the first of two lectures on axiomatizability. The material in these two lectures is rather special within the foundations of measurement. Much of it will only be familiar to students in philosophy or mathematics with some experience in logic. The first lecture will be fairly redundant to students with this background. I attempt to cover in an informal way the main topics in elementary logic needed to establish in the second lecture results on axiomatizability, both positively and negatively, that are of interest in the foundations of measurement. Also, there's been an attempt to start from scratch, so to speak. All of the concepts are defined and discussed, but of course many of the theorems that are needed, general theorems in logic, in order to establish particular results of interest in the theory of measurement, require substantial development. Consequently, there will be no attempt to prove any of the general theorems in logic. I do hope to have the time in the second lecture to give some sense of the way the proofs go for particular applications in the theory of measurement. So what we want to turn to in this lecture are the following topics. What we mean by elementary languages. Secondly, models of elementary languages. General theorems about logic. And when I say general theorems about logic, I have in mind general theorems about elementary logic, which we're going to characterize in a moment. Fourth, the more particular topic then of elementary theories. 5, some theorems and examples. And 6, some theorems on axiomatizability. Now let's begin with elementary languages. The idea of an elementary language is that we have restricted possibilities of expression. Intuitively, perhaps the central idea back of such languages is that the languages are about only one type of individual. Once that one type of individual is given, we can't specify and use higher types. For that reason, such languages are sometimes called in the literature of logic first-order languages, or also standard languages. We'll use throughout our discussion the term elementary languages, and this is what is used in the chapter on axiomatizability in Volume 2 of Foundations of Measurement. Now, the intuitive idea about being about only one type of individual is not as clear-cut as it might seem, because we can introduce a finite number of predicates, let's say 2 or 3 in many cases, that will permit us to define individuals having to satisfy that particular predicate. Well, let's take a concrete example that's a familiar one in elementary set theory. We might very well want individuals in the sense of concrete individuals in the world, and at the next level, the next type up, sets of such individuals, and then sets of sets, etc. Intuitively, we might want to think of the elementary language as only being about the individuals. But it's easy to introduce a predicate for being a set, and so we can require then of an individual now in quotes, which is either a true individual in the original sense or a set. Well, those that are sets satisfy a predicate like this. We could say X is a set if and only if either X is the empty set or there exists a Y and Y is a member of X. And then we can define individuals in the true sense of individuals we have in mind. X is an individual if and only if X is not a set. So as in many cases of logical matters, there are subtleties that don't seem apparent in the initial intuitive idea. All the same, it's important that from a formal or syntactical standpoint, we just will have one kind of variable and the quantifiers over just that one kind of variable. So, for example, we won't have quantification over predicates for every predicate P, for example. Given this intuitive idea, We want to turn then to a standard classification of the symbols of an elementary language. And we have 4 such classes of symbols. First are the logical symbols, and these are assumed the same for all the different elementary theories, for example, different elementary scientific theories that formally may be of interest in the theory of measurement. So the logical symbols, we have parentheses in their standard notation, sentential connectives, and I've just shown here the ones that will be the notation we'll use. In the case of not, sometimes we'll use simply a dash like this and sometimes a dash with a hook. Both notations are found in the literature. So that means it is not the case P, where P is some sentence. P and Q, where P and Q are sentences. P or Q, the wedge for or. If P, then Q. P if and only if Q. That notation is used widely now and will be familiar to most of you. We have variables. Next, now variables, remember, range over what are thought of intuitively as the individuals about which the language is expressing properties and relations. Variables will just be lowercase Roman letters with or without primes or subscripts. So x, y, x prime, y prime, x sub 1, y sub 1, z sub 1, etc. And finally, in the logical symbols, we have quantifiers. For every v, upside down a, and reverse e, existential, there exists a v, where v is any variable. We also have, and could properly place among the logical symbols, I've shown it here in the second class in the relation symbols, the logical predicate of identity or equality. We include that in our present framework as part of the logical symbols. The second class of symbols are, as I've started to indicate, the relation symbols, where for the official notation we will have only the case of the letter R, capital R, with or without primes or subscripts. But of course, as we work with the language, it's useful to introduce the standard informal notation, informally, and so we'll use familiar notation for binary relations, such as less than, equal to, or greater than, and for example, the ternary relation of betweenness for order on a line. Third class of symbols in the language, function symbols. Also, we'll often refer to, and you'll see referred to in discussions, the function symbols referred to as operation symbols. Now, in the official elementary language, we always have a single F, letter F, and we get distinct function symbols by adding primes or subscripts, as in the case of relation symbols. Informally, again, we'll use familiar operation or function symbols, plus, times, etc. The fourth category are individual constants. And again, officially, if we were writing down just the official notation, we would have the lowercase letter c, as usual, with or without primes or subscripts. Informally, again, we'll use familiar notation 0, 1, sometimes the constant e for the identity of a group, etc. One fundamental assumption, characteristic of elementary languages and elementary logic, is that the collection of relation and function symbols together with the individual constants form a finite set. Languages that do not have a finite set of symbols have a somewhat different character and will not be a topic that we shall discuss. Another way of putting it, we restrict ourselves to finitistic languages in this sense. Now, in order to characterize an elementary language, we want to characterize in sequence terms, atomic formulas, and formulas. And of course, then we think of formulas as being the basic as being the syntactical expression of the basic propositions of the language. First, terms. I'll go through this rather quickly. It's written out in explicit detail in the chapter, but the intuitive idea is important. We have, in all of these matters, a recursive definition. Any variable or individual constant is a term. And secondly, if f is an in-placed function symbol and t1 to tn are terms, then f of t1 to tn is a new term. Atomic formulas, we can take any two terms t1 and t2 and have them flank the identity symbol, t1 equal to or identical to t2, and that gives us an atomic formula. An atomic formula intuitively means a formula that has neither sentential connectives nor quantifiers. And secondly, if we have an in-place relation symbol and t1 to tn are terms, then r of t1 to tn is itself an atomic formula. The definition of formulas then is obvious. First, any atomic formula is a formula. And second, if P is a formula, then P and Q is a formula. And I've introduced here parentheses just to show how we would disambiguate in the absolutely careful and explicit language. P or Q, if P then Q, P if and only if Q, and the two quantified expressions for every VP, and there exists a VP, where P and Q are any formulas already given, and V is any variable. And that recursively defines formulas. Sentences of the language are formulas that have no free variables, so that they're quantifiers binding any variables that occur in the formula. Let's take a couple of examples of elementary languages. Take this familiar instance we're always discussing of order. So we have, in such a language of pure order, just a two-placed relation symbol, R. And an example of an atomic formula would be Rxy. An example of a formula would be if Rxy, then Ryx, or not Rxx. Now, informally, we would replace the notation Rxy by using the infix notation of the ordinary ordering symbol, x equal to or greater than y, and correspondingly in the other cases. Another example, the elementary language of the reals. In the informal symbolism, we'd have one relation symbol, less than, which in the formal, completely formal characterization would be a relation symbol R. We have two function symbols, plus and times, two individual constants, 0 and 1. And another and third example would be axiomatizations for groups. In one case, there are variants possible here. In one case, we would have a single two-place function symbol or operation symbol. That would be the only function symbol, relation symbol, or individual constant. Notice, of course, that the identity symbol or equality symbol is part of the logical apparatus. Another axiomatization of groups can easily introduce and have available the identity of the group. So that'd give us an individual constant. And still a third axiomatization can have both the binary operation of the group, binary operation symbol, the symbol for the identity of the group, and a one-place function symbol or operation symbol for the inverse of an object in the group. Let's turn now to the next topic, namely models of elementary languages, which takes us to a quick discussion, necessarily somewhat superficial, of the semantics of such languages. Intuitively, models of an elementary language are relational structures, just the familiar relational structures that we have studied throughout the foundations of measurement. Let's consider some definitions and some examples to make these ideas clear. And formally, we'll define a model in a different way initially, but we'll also refer simply later to a relational structure as a model. As we've already said, we're given the symbols of a language as a finite set. We've considered some examples. I've written down some more here. Here are the symbols of the real numbers, less than, plus, times, 0, 1. The symbol for a group just having the identity, just having an identity wouldn't be a group because we have no operation symbol, but just a single constant. A not very interesting theory. Here would be a symbol for a theory of pure binary order, just the binary operation symbol, and here would be a binary operation together with an operation symbol, the sort of thing that would be familiar in extensive measurement. Just the ordering relation and the binary operation of combination. Formally, we'll say that a model of a language L is a pair AV, where A is a non-empty set that we consider the universe of the model, or the domain of the model, we'll also say. And V is a valuation function defined in the set of symbols of L. V maps the symbols of L into the set theoretical objects that build up the model, that are themselves part intuitively of the relational structure. Let's take the case of the model for the elementary language of groups, where we have a binary operation symbol and an individual constant for intuitively the identity. Then the valuation function could be in a domain consisting of 0 and 1, V of the identity symbol could be 0, and the valuation of the operation symbol could be this simple matrix. It's important to note now that when we talk about the models of a language, the models of a language need not satisfy the axioms that we intuitively have in mind. Later on, we'll require that in talking about models of the theory. We want to distinguish in our language between models of the language and models of the theory. Models of the language are often, and in general won't be, models of the theory. Another way of putting it that's, I think, useful to keep in mind is models of the language just have to have the right set theoretical structure. Models of the theory have to have the substantive properties reflected in the intuitive relationships and concepts introduced in the theory. Now, there are some important general notions. Very important also to note that we define isomorphism is a theory-free notion, in the sense that we define isomorphism of models just at the level of models of the language. Another way of putting it is that the basic concept of isomorphism just uses the set theoretical structure and not any of the axiomatic restrictions or characterizations of the theory that we are interested in substantively. Isomorphism of models, this will be familiar, but let's put it in a rather detailed way for the present framework. There's even more detail and explicitness given in the chapter. So consider two models of a language L, A and A prime. We say that they are isomorphic. These are German A's, by the way, I'm using here. A and A prime are isomorphic if and only if there exists a 1-1 function phi mapping A onto A prime. Notice it's onto, such that, and the following three conditions need to be satisfied. For each in-place relation R of x1 to xn if and only if R prime phi of x1, phi of xn. Now, there's a point I've omitted here in what I've written down to reduce it. R prime must be the relation corresponding to R. What that means is that if we have a relation symbol in the language, then the value of R prime, the value of that relation symbol in model A must be R, and in model A prime must be R prime. That's a notion I'll call corresponding. That's spelled out in the chapter. And for F and F prime corresponding as functions, in-place functions, then phi of F of x1 to xn must equal F prime of phi of x1 to phi of xn. And same thing for individuals, that if C and C prime are individuals corresponding in the two models, that is, they each designate are designated by the same individual constant in the language of L, then we must have phi of C equals C prime. A very important notion of measurement, because in so many cases, as we've already discussed in other contexts, we are not interested in isomorphism because we'll be mapping distinct empirical objects into the same numerical representation. We want the more general notion of homomorphically embeddable or homomorphic to. So one model is homomorphically embeddable in another, or one model is homomorphic to another. And What we have in mind here is then that phi, the function phi, is not necessarily 1, 1, or onto. An important point to note is that this way of characterizing homomorphism, what we say about the function phi or phi, say both ways, it's stronger condition than in standard model theory. In standard model theory, condition 1 here, when we talk about homomorphism, is not if and only if, but if R, etc., then R prime. So this condition that we use throughout the foundations of measurement for homomorphism is stronger than you'll find in the model theoretic literature of logic. I think there are some special reasons for that strength here because of the intimate way in which we want to relate empirical relational structures and numerical relational structures. Next fundamental notion, A prime is a submodel of A, and that's just true when the relations and functions and domains of A are restricted to A prime, the domain of A prime. That's spelled out again in the chapter. I won't go over it in detail. We say that a model A is a finite model when? Just when its domain, as you would expect, just when its domain A is finite. Correspondingly, the model is infinite just when the domain or universe of the model is infinite, that is a set that has infinite cardinality. The central concept of model theory is the concept of a formula of the language L being satisfied or being true in a model of L. We're not going to give a formal definition of this because the notion of being true is intuitively very strong, strongly present in a vivid sort of way from examples, as we'll see. The formal definition of satisfaction is rather complicated and would be distracting in terms of our main objectives. It's in the literature. It's not in the chapter, by the way, because we're going to rely on the same intuitions in the chapter that we are in this lecture. Notice that being true is all we need for sentences with no free variables. When we have formulas with free variables, we need the general notion of satisfaction. But that's something that we can avoid without any real loss of clarity, both in these two lectures and in the chapter. That is the problem of giving an absolutely rigorous and formally explicit characterization of satisfaction. Let's consider some examples, and we'll see how vivid and natural this notion of a formula being true in a model is. Let's consider the most trivial example we possibly can, almost. We'll take a one predicate, one place relation as the only symbol of the language L. So we'll have R and it's one place. And we'll take as a model the set A. Will have the two objects, the numbers 1 and 2. And then the valuation function for the symbol R will be V of R is just a set consisting of 1. Now let's look at a number of formulas and see how easily we can decide whether true or false. All these formulas, of course, will be sentences because I won't leave any free variables. First sentence, there exists an X, Rx. Now notice the notion of truth here is very vivid, but of course it's truth relativized to this particular model. So we ask, is the statement there exists an X, Rx true in the model A that I've given? And the answer is yes, because the number 1 has the property R. Second question, so we can mark true under this one. Second sentence, for every X, Rx, is that sentence true in the model? Answer no, because 2 doesn't have the property R. So it isn't true for every X. X now ranges over the numbers 1 and 2, the domain of the model. So this is false. Third sentence, more complicated, there exists an X, there exists a Y, X is not equal to Y, and Rx and Ry. So that says there are at least 2 objects, distinct objects, with the property R in the model. And that's false, of course, because only 1 has that property. So we label that false. And finally, we have the sentence, there exists an X, it is not the case Rx. And that's true because the object 2 doesn't have the property R and therefore satisfies that formula. So that is true. And I hope those examples are absolutely crystal clear. They're utterly trivial, and they're meant only to illustrate notation and ways of talking. Now, given this fundamental notion, there are subsidiary notions we define in terms of it. First, given a set of sentences of L, we say that A is a model of S, that is a set of sentences. A is a model of S if and only if every sentence of S is true in O. You can see how we're going to generalize this. We can say A is a model of a theory if and only it's true of all the axioms of the theory. Two other notions. We say a sentence S of L is valid if and only if it is true in every model. You might ask yourself, what's an example of such a formula? That's obviously a logically true formula, the notion of valid. An instance would be, in every theory, for every x, x is identical to x. Nothing very interesting, but an example. More interesting is the concept of satisfiable. A sentence S of L is satisfiable if and only it is true in at least one model. And again, you might say, well, if we take all these formulas I went through in this very simple language L, they're clearly all satisfiable. We can change the model. Where this is false, we restrict the domain A to 1 and keep R being just the set 1, just being the other set 1. Then this become true. Now this would now be false, but we can change again the model to make this true. Well, the answer, of course, is sentences that aren't satisfiable would be sentences that are intuitively inconsistent. An instance would be there exists an x, Rx, and not Rx. So this would be an instance in our simple language of a sentence that is not satisfiable, because it clearly cannot be true in any model of the language. And any inconsistent sentence would be exactly of that character. All right, now we want to turn to some general results about logic that we'll use. In order to state these theorems and give a good sense of their content, we need the notion of a logic for an elementary language L. And this logic is to match the semantic notions. Intuitively speaking, the logic has a set of syntactic concepts corresponding to the semantic notions already discussed in talking about models of the language L. The notion of being a theorem corresponds to being valid. The notion of being consistent to the semantic notion of having a model. And the rules of inference by which we prove theorems or show something's inconsistent corresponding to the notion of logical consequence. I didn't formally define logical consequence earlier in the lecture. P is a logical consequence of Q if whenever Q is true, P must be true. And we have a corresponding notion then in inference. It's familiar in the logical notation to use this symbol for being a theorem with the single bar, horizontal bar, and this symbol for being valid with the double bar. And we say here that P is derivable from a set of sentences F, single bar, horizontal, with the F preceding the vertical bar. And over here, P is the logical consequence of a set of sentences F, S. These are general and notions that they intuitively correspond to what we would think, except there is one important, in a certain sense, unsatisfactory feature about a logic. The notion of logical consequence essentially has one classical intuitive characterization. But the rules of inference can vary, and there are many variants, there are slight variants, in the literature. Exactly how the rules of inference are stated and how a set of restrictions is imposed on the rules of inference in order for them to be sound, that is, not to lead from true premises to false conclusions. I won't discuss any of that, and we won't need to use any details, but it is important to note that in terms of the actual working out of a set of rules of inference, there is that aspect of it that has to be dealt with. Now, there are 3 or 4 more theorems stated in the chapter of a general logical nature than I'll go over here. I'll just mention the ones that are most important for our subsequent discussion. But I recommend you look at this section of the chapter for more details, and especially for some other theorems. The first one is Gödel's completeness theorem. Now, Gödel's completeness theorem is to be clearly distinguished from his famous incompleteness theorem for arithmetic. This is his well-known completeness theorem for elementary languages. Given a sentence P of an elementary language L, P is a logical theorem if and only if P is valid. Another way of putting it is that the rules of inference in a elementary language can be both sound and complete. What is important is the notion of completeness. That is, if a theorem is valid, then we can have a logical derivation of it. That is the strong sense of completeness. Now, there is a second very closely related theorem of Gödel's called the extended completeness theorem often, and that is that a set S of sentences of an elementary language L is consistent if and only if S has a model. I haven't said how we define consistent in a syntactic way. There are several ways of doing it. One is that a set of sentences is consistent in the logic if and only if not every formula of the language can be derived from the set S. Notice that we need a syntactical definition in terms of derivation in order for the theorem to have content, because what the theorem does is relate the syntactic notion of consistency with the semantic notion of having a model or being satisfied in a model. Now, directly for some results in the theory of measurement that we'll want to discuss and put some stress on is the famous Lowenheim-Skolem-Tarski theorem about the cardinality of models of a theory. This theorem asserts that if a set S of sentences of an elementary language L has an infinite model, then it has a model of every infinite cardinality. Now, this leads to what is sometimes the famous Lowenheim, as it's called, the famous Lowenheim-Skolem paradox. Let's consider an example, maybe 2 examples. If we have an elementary axiomatization of the real numbers, then what the theorem asserts is that it will have, that is, the theory of the real numbers, the elementary theory of the real numbers, must have a model of countable cardinality. That is, all models of the theory are not going to be of the intuitive cardinality you would expect. And that's sometimes thought of as paradoxical. A second example, if we axiomatize set theory, and within set theory we can develop the theory of the real numbers, and that's a standard thing in a course in set theory. If the theory of sets is elementary in the sense of an elementary being within an elementary language, a set of sentences, the axioms, for example, are a set of sentences in an appropriate elementary language, then the Lowenheim-Skolem theorem is that we must have a countable model. Now, the theorem is called the Lowenheim-Skolem-Tarski model because Tarski noticed that we could have the so-called upward Lowenheim-Skolem theorem, namely that the cardinality not only in these cases that I've been mentioning can come down, that is, from the intuitive model with the cardinality of the continuum down to a countable model, but if we have a model that's, for example, of the cardinality of the continuum, then in every other larger cardinal must also have a model of that cardinality of the theory. And this is of interesting from the standpoint of the theory of measurement, because it means that intuitively, and we'll go into this in more detail in the second lecture, but intuitively, if we have infinite models of an elementary theory, and we cannot get then just isomorphism into the real numbers, because there'll be too many objects in possible models of the theory, namely There'll be models of very large cardinality, and unless we are able to map many different individuals in these models into the same real number, there'll be no hope of having representing numerical structures of elementary theories that have infinite models. We'll say more about that later. Now, we go on to the next topic, very closely related to what we've been saying and talking about, the topic of elementary theories. An elementary theory T of an elementary language L, or we'll just say a theory T often of an elementary language L, but we'll often talk about just say the elementary theory, is a set S of sentences of L that is closed under logical consequence. Now, we can then talk about models of a theory satisfying T, and that is simply models that satisfy this set of sentences of T. The set of sentences that characterize T. Now, in order to talk about axiomatization of an elementary theory, we sometimes need an independent way of talking about what it means for a sentence to be valid in a theory. Clearly, if we have the axioms at hand, we can say, well, a sentence is valid in the theory, we might say, if and only if it's derivable from the axioms of the theory. And in view of Gödel's completeness term, we might well be satisfied with that. But in general, we want to study the question of axiomatizability. Consequently, we will want an independent way of talking about validity. And so we'll say that a sentence can be characterized as true in a given model or class of models, and that's what it means for a sentence to be valid in a theory. So, for example, I might give a particular model of, say, a binary ordering relation. Then the theory would be made up of all the sentences that are true in that particular model. Now, often, instead of having a single model like that, I'll have a class of models. But the point is that we characterize valid sentences of the theory. Now, not valid sentences of the language, notice. Valid sentences of the theory by being true or being satisfied in some model or class of models. Now, another way is in terms of axioms, and we want to turn to that. Well, we can say S is valid, a sentence of a theory T, if and only if what? S is an axiom or it's a logical consequence of the axioms. And what we're really after now is a discussion of axiomatizable under various conditions, axiomatizability. So I'll quickly go through 4 or 5 definitions and then give some illustrations. These definitions are weaker and stronger notions of axiomatizability. We say the theory is axiomatizable when a set of axioms can be given. Now that is, when a set of axioms can be given from which all valid sentences of the theory can be derived. We say that the theory is recursively axiomatizable if and only if there exists a recursive set of axioms. Now, notice what's important about recursiveness here. Ordinarily, in our intuitive thinking, we say that we think of axioms as being recursive. That means that we have a mechanical procedure for recognizing when a sentence is an axiom. Theories that are axiomatizable but not recursively axiomatizable are not very interesting. That is, the axioms aren't very interesting, certainly. The theories may be interesting and often are for other reasons. But intuitively, in the ordinary world, when we talk about axioms, we ordinarily require that the axioms form a recursive set. So we can tell whether or not a sentence of the language mechanically, by a simple mechanical decision procedure, does or does not belong to the set of axioms. A more restricted notion is that of finitely axiomatizable. A theory is finitely axiomatizable if and only if there exists a finite set of axioms. And a more special notion now of some importance in the theory of measurement, as we'll see in the second lecture, a theory T is universally axiomatizable if and only if there exists a set of axioms for the theory that are all universal in character. That is, that only universal quantifiers occur, and they all occur standing at the beginning of sentences with scope the remainder of the sentence. We'll also put these two notions of finitely axiomatizable and universally axiomatizable together sometimes and talk about a theory being axiomatizable by a universal sentence. Because if the universal sentences are finite in number, we can just take their conjunction to get a single sentence. All right, let's consider some examples of these concepts. What about the theory of weak orders homomorphically embeddable in the real numbers under the natural ordering? That's a theory that would be natural for us to consider in the theory of measurement. And we might ask, and we studied that in fact in the lecture on ordinal measurement, we might now ask, can that theory be given as a theory that is elementary in the strong sense of elementary set forth in this lecture? The answer is no. That the theory is not even axiomatizable. So what this means is that the axiomatic characterization we gave of such orders in terms of having a countable order-dense subset in the lecture on ordinal measurement, that cannot be replaced by a collection of elementary sentences. On the other hand, consider group theory. Groups or the elementary theory of groups is not only axiomatizable and recursively axiomatizable, but finitely axiomatizable. And in particular, if we have all of the symbols that we sometimes want, so we have not only a binary operation symbol, but an identity and an inverse operation, then it's axiomatizable by a single universal sentence. And I've written down the three sentences here without any quantifiers that we can conjoin and quantify in front with for every x, y, and z. So we have just associativity, the identity axiom, and the inverse axiom. So by just taking the conjunction of these three, we have axiomatizable by universal sentence. That's obviously, in a certain sense, the most restricted concept we've introduced of axiomatizability. In general, theories as we ordinarily formulate them are not axiomatizable by universal sentence, but many simple elementary theories are. Another example beyond this would be the ordinary elementary axioms for an ordered field, where we introduce the identity element for addition, the identity element for multiplication, and the inverse operations. I now want to turn to a topic that needs to be introduced here and that I forgot to mention in the introduction, namely the general concept of definability and interpretability. There are only a few things to be said about definability and interpretability in the short time we can devote to this, but there are a couple of central points. First, what is the logical status of a definition? In talking about elementary theories, we talked as if all the symbols that were introduced were always introduced at the beginning as primitive symbols. But that's not ordinary mathematical practice, and we can have a methodology for introducing definitions, but of course we simply can't introduce anything as a definition. There are two classical criteria we expect a definition to satisfy. These are the criteria of non-creativity and eliminability. Let's take a look at what these mean. Non-creative means that if I introduce a definition, I can't now prove something in the original notation I could not have proved without the definition. A very simple example can be given from taking as axioms for semigroups with identity. So we just have two axioms, associativity and the property of the identity, where we'll also want to make it, for this purpose, a left identity as well. And now we introduce the improper definition of inverse. X combined with X inverse is equal to E, where this sentence is meant to define the inverse operation. Well, it's clear that that's an improper definition because we can then prove in the original notation that there exists a Y that for every, I have those quantifiers wrong, let's correct that, for every X there exists a Y such that XOY is equal to the identity element. And of course, just given the two axioms for semigroups, we couldn't prove that. It's easy to give other examples. In the case of operation symbols that are introduced, in general we have to be careful about existence and uniqueness in not letting them be non-creative and letting them be creative, that is, we want them to be non-creative, or in having the property of eliminability. Here's a simple sort of example. Suppose in our elementary axioms for number theory, we introduced the star operation, x star y equals z if and only if x identical to y and z equals z. Then we immediately have as instances of the definition 2 star 2 is equal to 2 and 2 star 2 is equal to 4. So we have immediately 2 is equal to 4, which would be a contradiction. Well, there's more detailed discussion, and in particular, there is a discussion of rules of definition that will guarantee that these two criteria of non-creativity and eliminability are satisfied. Intuitively, in ordinary mathematical practice, as for example in the way measurement theory is done in the rest of these lectures and in the 2 volumes, these criteria are satisfied. But they are satisfied, so to speak, ordinarily without thought. It's useful to bring to the surface what kind of criteria need to be satisfied by a good definition. The notion of interpretation is a very intuitive notion of interpreting one theory in another stronger theory. For example, we can interpret the theory of weak orders in terms of the theory of simple orders, but not conversely. I'm not going to give the formal definitions, but urge you to look at them in the chapter. I do want to use 1 or 2 notions of interpretability in the theorems that we discuss at the last topic in this lecture. So with that very breezy and superficial survey of definability and interpretability, let me go on to, for the first time in our discussion of axiomatizability, some theorems that have a direct application to measurement. And for that purpose, we need some external way of talking about measurement structures. So we want to define what we mean for a class of models of an elementary language to be a class of measurement structures. So the class must be non-empty, say the class K, and must have 2 characteristics. K must be closed under isomorphism, and secondly, there exists a numerical model R of L, that is of the given elementary language, such that every model of this class K is homomorphically embeddable in R. Now, given such a characterization of K, which gives us an external way of talking, there are 2 theorems that I want quickly to discuss. The first is that the class of models of any elementary theory that has infinite models and is such that the theory of simple orders is interpretable in it is not a class of measurement structures. What this says is that if we have the theory of simple orders within the theory, which we almost do, and we have infinite models, then no elementary theory can be a theory of measurement structures. And of course we prove this by using the Lowenheim-Skolem-Tarski theorem, that if we have an infinite model, we have a model of arbitrarily high cardinality, and with simple orders, any homomorphism must be 1-to-1. It can't not be other than 1-1, and consequently we could not have the condition for being homomorphically embeddable in the reals, because it would violate the Lowenheim-Skolem-Tarski theorem. Now, the unsatisfactory character of this theory, from the standpoint of theory of measurements, is that we actually use ordinarily weak orders and not simple orders, because distinct objects are assigned the same place in the order. And this can be avoided. It requires a little more technical discussion. We get essentially the same theorem, and those detailed developments are to be found in the chapter. But the intuitive idea is already caught directly in this simple theorem, and the proof intuitively is quite obvious from the Lowenheim-Skolem-Tarski theorem. It's spelled out in the chapter. The other theorem, on the other hand, is a positive theorem about finite models. We say that a class of models is finitary if and only if each model in the class is finite. That is, the domain of each model is finite set. And the theorem we have about axiomatizability is that any finitary class of measurement structures of an elementary language is axiomatizable, but not necessarily recursively axiomatizable. So this means that if we restrict ourselves to finite models, then the theory is axiomatizable. The proof of this goes in a fairly direct way by showing that we can have a recursively enumerable procedure for enumerating the valid sentences, that is, the sentences that hold in the structures of K. Of course, note, the result for practical purposes is not going to give us, in general, an interesting axiomatization, because we aren't even guaranteed that we have a recursively axiomatizable theory. What is important, though, is it does distinguish a wide class of theories that are axiomatizable, because, as we'll see, in the case of infinite models, they aren't axiomatizable at all. I'll continue exactly on these general problems in the second lecture on axiomatizability.